This is my intermediate algebra course. Today we're going to continue to learn roots. If you haven't done the homework completely and correctly from last class, do that homework before watching this video. Now we're going to start by learning some vocabulary. You know that this number here is called a power, but it's also important to know that this number is called the base, and we're going to use that in class today. Now you know that this number over here is called the index in the root symbol, but it's also important to know that this number is called the radicand under the root, and the root symbol itself is called a radical symbol. So if you take the square root of 4, the number that you get, that's actually technically the root. Okay, but the actual symbol that you use to find the root, that's called the radical symbol. And of course 4 is the radicand, and the number in here, we don't see any number, but whenever you don't see a number, it's assumed to be 2, so the index is 2. So this is all stuff that we're going to use today, and you can take a screenshot of that if you want. Now, we're going to talk about raising a negative number to an even or odd power. So we're using -2 as the base. That's the negative number we're raising. And it turns out that when you raise a negative number to an even power, you see these even powers? When you raise a negative number to an even power, you always get a positive number. So you see the positive numbers, 4, 16, 64, we always get a positive number. All right. Now, if you raise a negative number, again using -2 as an example base, if you raise a negative number to an odd power, you see these odd powers? If you raise to an odd power, the answer is always negative. Again, assuming that your base is negative. In this case, the base is -2. So we're going to use that in class today. So let's go on to negative variables under radical symbols. That's what we went over all this previous stuff just to prepare you for that. So now what we're about to go over is something that can be really confusing to students, and for that reason a lot of teachers, they just skip it completely. And I'm not going to go over this a lot, but I do want you to understand the basic principle. So remember in the previous classes we learned that the square root of x squared is x. Okay, but we assumed that the variables were positive. Remember when I wrote in red, we have to assume that, the unknowns or variables, whatever you want to call them, are positive, So we're assuming that all variables are positive in the previous classes, but in this class we're not going to assume that x is positive. It might be negative. If x is negative, then this is not true. And let me tell you why that is. If x is negative, then you have to put absolute value signs, then it would be true. So why is that? Well, let's let x equal, so we're going to make an example here. Let's let x equal -5. So then, if you take that expression there, and you plug in -5, again, if you just write it this way, you end up with -5. If x is -5, then the answer is going to be -5, but that is wrong. Why is that? Remember, with the x, when you have x, you just counteract the 2. The 2 goes away, you're just left with x. Well, here's why it's wrong. It's just an order of operations thing. Mathematicians, they come up with rules, and we have to follow those rules. It's like when you play a board game or something, there's rules to the game. Once you determine what the rules are, you have to follow the rules. Okay? And you can't just change the rules in the middle of the game. So that's the way it is with math. In order to learn once you learn the language, you have to follow those rules. So the rules tell us it's all about order of operations. Okay? So order of operations tells us that we have to do the inside part first. So what that means is that the square root of -5 squared is going to be square root 25, doing the inside part first. So we squared the -5 part first. Then you take the square root of 25 to get 5. Okay, so that's an important rule, and the reason that a lot of students are confused by that is the textbooks, they talk about order of operation, but they don't really talk about it in a lot of detail. In fact, when you're doing just multiplication and division, you have to go left or right. When you're doing addition and subtraction, you have to go left or right. A lot of books don't even say that, even though, that's the way it is. And when it comes to this stuff, the order of operations agreement doesn't really talk about it much. So students don't really even know about it. The textbooks don't even talk about it. So that's why this is really confusing for students. Another reason it's confusing for students is that when you take a square root of a number, let's say you take the square root of 4, we know that that's going to be 2, because you're asking what number times itself is equal to 4. But here's a problem. Wouldn't negative 2 work also? If you multiply 2 by itself, you get 4. But if you multiply negative 2 by itself, negative 2 times negative 2, you also get 4. Why is it that 2 is the only answer? Well, this is another thing that textbooks typically don't talk about. The reason that it's only 2 and not negative 2 is that, and I think we talked about this previously, the reason is mathematicians have defined this square root symbol to only produce a positive number. That's just their rule. It only produces a positive number. And you might be thinking, well, how come? Well, again, you just define the rules and then you have to follow the rules. That's what mathematicians have decided. So those are the two things that we need to consider. Number one, you do the inside part first. And number two, a square root can only produce a positive number. So for all those reasons, this doesn't work. It's not true if x is a negative. And this doesn't work because, again, that's an example where x is negative 5 and it just doesn't work. The reason it doesn't work is because you have to square the inside part first, which gets rid of the negative. Now you don't have a negative anymore. Then you square root that and you get a positive. But here, you see up here, we have negative numbers. So if you assume that x is negative, and again, we don't know if x is negative or positive, but let's assume that it's negative, okay? Meaning you can't assume that it's like in the previous class we assumed it was positive. Let's assume that x is negative. If you raise it to the second power, again, you have to do the inside part first. If you raise it to the second power, it's going to turn positive. But then if you square root it, that's not going to do anything. That's going to keep it positive. So our answer should be positive. Even though the base is negative, it starts out negative, our answer should be positive. But it's not positive. Because remember, if our base is negative, then that means that this answer is telling us the answer is negative because x was negative. You see, I know this is very confusing. But again, the reason that this problem occurs is because we can't get rid of the negative when we square it because we don't even know what x is. How can we get rid of the negative? All we can do is just say, well, this square root counteracts the power and we end up with x. But the problem is, if x is negative, the negative should have gone away. But because x is negative here, you're saying that your answer is equal to a negative number. It can't be negative. It's supposed to be positive. So what we do is we simply get rid of that not equal to sign, and we put absolute value symbols, and that's it. That's how we solve the problem. So again, I know that's very confusing, but well, I guess I can just keep that there. It's summed up in this statement here. And as you do practice problems, you're going to understand why or what this is. You can get a screenshot of that if you want. It's important, and you're probably thinking that this sounds really complicated, but there's good news. The good news is that this problem only occurs when you have an even index on each one of these roots. Okay. So if you have an odd index in the root, for example, if you have, cube root or fifth root or seventh root, you don't have to worry about this problem at all. You don't have to worry about absolute value symbols. Okay. And when it's an even root, you have to worry about it sometimes. It's not even every situation where you have to worry about, putting absolute value symbols. So that's the good news, is that you don't have to put absolute value symbols on every answer. So let's do this example. Again, if you don't understand this, that's okay. You're going to understand as we go along here. And notice it says, do not assume that the unknowns are positive. Okay. So in the previous classes, we assumed that the variables were positive. We're not doing that here. Okay, so the first question you ask is the index even or odd? Well, remember, if there's nothing there, if there's no number, it's assumed to be 2. Okay, I think we talked about that in the previous class, but it's assumed to be 2. So the index is even. Okay, that means that we do have to worry about absolute value symbols. Okay, if we're doing this problem, we don't have to worry about absolute value symbols because the index is odd. All right. So this problem you would just do like you did in the previous classes. So we take the power of the radicand, divide by the index. 14 divided by 2 is 7. All right. But because we have an even index, we do have to worry about whether or not we put absolute value symbols. Now, listen very carefully. If you didn't understand that whole explanation, this is where it's going to start to click. Now, we have to assume that x is negative. We don't know if it's negative or positive, but we have to assume that it's negative so we don't make a mistake here. Now, isn't it true that when you take a negative number and you raise it to an even power, it becomes positive? That's what we went over here. Remember, if you're raising a negative to an even power, the answer is always positive. So isn't it true that, again, this is a positive number because you're raising a negative number to an even power? So now you take the square root of that positive number, and of course your answer should be positive. This answer should be positive based on all this, all these operations. Again, we're just following the rules. That's all we're doing. We're following the rules of all these operations. So our answer should be positive, even though the base we are assuming is a negative. Okay, again, we don't know what the base is. It could be negative or positive, but we're assuming the base is negative. Even though our base is negative, the answer is positive. Okay, but here's the problem. If x is negative, then that means when you write this expression, this is negative. But if you raise it to an odd power, this answer is negative. So we're not supposed to get a negative, so we have to put absolute value symbols. Again, I know that's really difficult to understand. There's a lot going on there. It's not really difficult. It's just that, students get confused because you're throwing a lot at them all at once. But again, when you have an odd index, you don't have to worry about any of this. You just take 9 divided by 3 and you get x to the third power. Okay, so now let's do another one. Now here we have an even index again. The index is 2. So we have to worry about possibly putting absolute value symbols. Now take the power of the radicand, divide by the index. 4 divided by 2 is 2. So that's our answer. Now, because this is an even index, again, we have to worry about whether or not we put in absolute value symbols. So do we put absolute value symbols? That's the question. Well, first of all, again, if x is negative and you raise it to an even power, the inside part has to be positive. Then you take the square root of a positive number, and it's going to be positive. So this is telling us our answer has to be positive. So again, assuming that x is negative, do we have to worry about this being the wrong sign? And the answer is no, because even if x is negative, this even power is going to make it positive. So we don't have to write absolute value symbols. So the general gist here is if the index is even, but the power in your answer is odd, then you have to worry about, excuse me, this is odd, not the other one. Then you have to worry about putting absolute value symbols. But if your power is even in the answer, you don't have to worry about putting absolute value symbols. Again, I know it's a lot to take in. Okay, on this problem we have an odd index, so we don't have to worry about absolute value symbols. And the answer is going to be x. So the fifth root just counteracts the 5 power. I mean, it's just asking, a fifth root means what number times itself, and times itself again, and times itself again, and times itself again is equal to x to the fifth. Well, that's obvious. It's just x. So that's how we got that answer. I don't think we did fifth powers in the previous classes, but it's all the same type of, it's the same type of operation. Again, because we had an odd index, we don't have to worry about putting absolute value symbols. Now we have an even index. We have to worry about absolute value symbols. All right, so the fourth, you just take the 4 divided by 4, the power of the radicand divided by the index. 4 divided by 4 is 1, so it's just x to the 1 power. But x to the 1 power you can just write as x. Okay, so do we have to put absolute value symbols? Well, the power is odd. 1 is an odd number. So you do have to put absolute value symbols. Okay. So again, just to remind you, if we assume that this is negative, because we don't know if it is or not, so we have to assume that it's negative. When you raise it to an even power, it becomes positive. Okay? And then you take the fourth root, and that's not going to change it to a negative. So our answer has to be positive. But wait a second. If x was negative, or if we're assuming it was negative to begin with, then this is obviously not positive because x is negative. Our answer was negative, so we have to change it with these absolute value symbols. Okay, so we're going to do one more of these before you try some on your own. So the first question you ask is, is the index even or odd? The index is even. So what that means is that we do have to worry about absolute value symbols. Now you take the power of the radicand, divide by the index. 16 divided by 4 is 4, so x to the fourth power. But now we have an even power. So if x ends up being negative, it doesn't make any difference because, we're just going to raise it to the fourth power. It's going to turn to positive. Now you might be thinking, well, wait a second. What if we get, like fourth root of x to the 15th power? What if we get that situation and x is negative? Well, you don't have to worry about that. Because if you raise a negative number to an odd power, the answer is going to be negative, and then you have negative inside, you have a negative number inside an even power root, and that's actually undefined. Okay, we're going to talk about that later on in this class. All right, so go ahead and try number 7. Remember, the first question you need to ask is it an even or odd index? All right. And if it's an even index, that means you have to worry about the absolute value symbols. And it's always going to be this number divided by the index. So we know it's going to be x to the 11th, but you have to figure out, do we put absolute value symbols or no? So do number 7, and when you come back, we'll do it together. All right, we're back. So it's an even power, which means we do have to worry about the absolute value symbols, and we're left with an odd power, so we do have to put absolute value symbols. Now for number 8, this is an odd index, so that means you don't have to worry about the absolute value symbols. So try number 8, and when you come back, we'll do it together. All right, we're back. So we don't have to worry about the absolute value symbol, so we just do 15 divided by 3 is 5, and we get x to the 5th. All right? So do number 9, and when you come back, we'll attempt it together. All right, we're back. So it's an even index, so we do need to worry about absolute values. So you just take the power of the radicand, divide by the index, and you get x to the 8th power. And so now we have to think, do we need absolute value symbols here? Well, we have an even power, so even if x ends up being negative, it's not going to turn, or the power is not going to keep it negative. It's going to turn it to a positive when you raise it to the 8th power. So if you got those answers, good job. Try number 10, and when you come back, we'll do it together. All right, we're back. So first question we need to ask is, is it an even or odd index? It's an odd index, which means we don't really need to worry about absolute value symbols. We just take the power of the radicand, divide by the index. 14 divided by 7 is 2, so we have x to the 2nd power. And that's our answer. Again, we don't have to worry about absolute value symbols because the index is odd. All right, try number 11, and when you come back, we'll do it together. All right, we're back. The index is even, so we do need to worry about absolute value symbols. You take the radicand, divide by the index. 20 divided by 4 is 5, so we have x to the 5th power. Now, this is an odd power, so we do have to put absolute value symbols, you see. Again, I know this stuff is very confusing, but all this means is that if x is negative and you raise it to an even power, it's going to turn positive, and the root is going to keep it positive. Our answer has to be positive. Even though the base was negative, our answer has to be positive. So we can't just write x to the 5th power, because if x is negative, this is when you raise it to an odd power, it's going to be negative. Our answer can't be negative because we use this logic to find out it should be positive, you see. So we have to put the absolute value symbols. Again, I know this is very confusing, but it's really just, as long as you know the rules, as long as you know the rules of the game, the order of operations, then what this symbol means, then it's really not that difficult. So try number 12, and when you come back, we'll do it together. All right, we're back. So the index is even, so we definitely need to worry about we need to worry about absolute value symbols. So we take the power of the radicand divided by the index, and we get x to the second power. But even if x is negative, it's just going to turn to positive once you raise it to the second power because it's an even power. So if you got those answers, good job. Okay, so we're just going to do a few more of those problems just so you get the hang of it. Let's do these together. So we're going to separate this root into two roots, two perfect squares. The square root of 9 is 3. And now you have to ask yourself, is this an even power? And it is, so we might have to worry about absolute value symbols. Now you take the power of the radicand divided by the index. 6 divided by 2 is 3, so we have x to the third power. But look out, this is an odd power. So, because we have an even index, we should have, as long as there's a positive inside here, we should have a positive answer. So we have to change it to positive. Because if you raise a negative number to a odd power, you get a negative, but we can't have that. We know our answer has to be positive. Okay, let's try another one of these. So let's see, we're going to have to factor first. So that becomes 9 times 2 times x to the 8, which equals square root of 9 times square root of 2 times square root of x to the 8. And then square root 9 equals 3. And we can't do anything with that. And then we have an even power here, you see, so we're going to have to worry about absolute value symbols. But you take the power divided by the radicand, or divide by the index. 8 divided by 2 is 4, so we have x to the fourth power. But this is an even power, so we don't have to worry about absolute value symbols. So we just put those together, and we're done with that one. No absolute value symbols necessary. Again, this seems very difficult, but you'll get the hang of it as we go along here. So let's do a couple more of these before you try one on your own. Now we're doing a fourth root, so you want to factor. 256 is a perfect fourth power, so we don't have to do anything with that. But we do have to factor x to the 6th to x to the 4th times x squared because this is a perfect 4 power. So now we separate and we get fourth power of 256 times fourth root of 256 times fourth root of x to the 4th times fourth root of x squared. Okay, so the fourth root of 256, that's going to be 4. And the fourth root, and now we have an even power, so we have to worry about the absolute value symbol here in this variable. And so we take the power of the radicand divided by the index. 4 divided by 4 is 1. And the question is 1 an odd power? And yes, it is an odd power. So we have to put absolute value symbols around it. And the other part we can't do anything with. And then you're done. All right. On to the next problem. Now number 16. This is the last one we'll do together, and then you can try some on your own. So we have a 6th root, and that's an even root. So we're going to have to worry about the absolute value symbols. We take the power of the radicand divided by the index. 18 divided by 6 is 3, so we have x to the third power, but this is an odd power, so we have to write absolute value symbols around it. Now it's time for you to try some of those slightly more difficult problems. So go ahead and try. You can take a screenshot of these if you need to use these to help you. And go ahead and try number 17, and when you come back, we'll do it together. All right, we're back. So we're going to factor. 49 is already a perfect square, and actually x to the 10th is already a perfect square too, so we can go ahead and just break apart. And so square root of 49 is 7. But now we're going to have to worry about this because we have an even root, even index. So now we take the power of the radicand, divide by the index 2, and then we get x to the 5th. So again, the power of the radicand divided by the index. 10 divided by 2 is 5. This is an odd power, so we have to put absolute value symbols around it. All right? So if you got that answer, good job. And you don't really need the dot. You're not going to see the dot in the answers to in textbooks and whatnot. Okay, so why don't you try number 18, and when you come back, we'll do it together. All right, we're back. So we're going to factor to 4 times 5, and x to the 4th is already a perfect square. And we're going to separate, and square root of 4 is equal to 2. Square root of 5, you can't do anything with that. And this is an even index, so we have to worry about absolute value symbols. So take the power of the radicand, divide by the index. 4 divided by 2 is 2. So we get x squared, but since that's an even power, we don't have to worry about absolute value symbols. So our final solution is going to be 2x squared times root 5. It's always good to write the numbers outside the root in front, or else it could be really confusing. Okay, so on to the next problem here. I'm going to move this over a little bit. Okay, try number 19, and when you come back, we'll do it together. All right, we're back. So we have the, let's see, 81 is already a perfect 4 power, so we don't have to factor that, but we do have to factor x to the 6th times to x to the 4th times x to the 2nd. Now we're just going to break up into parts. And the 4th root of 81, that's just going to be 3. And now we have an even index, so we have to worry about absolute values. So take the power of the radicand, divide by the index, you get 4 divided by 4 is 1. So we have x to the 1 power, but that's an even, or excuse me, that's an odd power. So we have to write absolute value symbols around it. And then we can't do anything with the 4th root x squared. So if you got that answer, good job. Okay, so again, I'm not going to spend a lot of time with this. So if you're hating this thing, then don't let it bring down your whole roots curriculum. It's not something we're going to spend a lot of time doing. It's not going to be a big part of the class. So go ahead and try number 20, and when you come back, we'll do it together. All right, we're back. So this is an even index, so we're going to have to worry about absolute values. And so we just take the power of the radicand, divide by the index. 8 divided by 2 is 4, so we have x to the 4th, but this power is even, so even if x is negative, it's gonna change it to a positive. So if you got that answer, good job. We don't need absolute values on number 20. All right, so now we're going on to imaginary numbers and complex numbers. But first, imaginary numbers. Now, an imaginary number is a number such that when you square it, you get a negative number, -1 specifically. So when you square I, you get -1. Now, do you see a problem with that? That's impossible. How can you square a number and get a negative number? If x is positive, then obviously you're not going to get a negative. And if x is negative, then you're multiplying a negative by itself. So a negative times a negative has to be a positive, right? That's just stuff that we learned in pre-algebra and beginning algebra and so on and so forth. But I, if you square I, it equals a negative 1. So that's why I is called an imaginary number. That's what I stands for, imaginary. It's imaginary because it breaks the rules that mathematicians have put forth. And so you're probably wondering, well, why are we defining this term? Again, this is what the definition of I. It is square root -1. Okay, so if you square I, that's the same thing as multiplying root -1 times root -1. And that's the same thing as root -1 squared. The square is just getting rid of the square root, and you just have -1. All right. And the rules don't always work with this. For example, you might say, well, wait a second, root -1 times root -1. If you use the principle root A times root B is equal to root AB, like we did in previous classes, then doesn't the negative go away? Because root -1 times root -1 is root negative 1 times negative 1. Sorry about that. I'm going to move that over. So the inside part becomes positive, and you just get root 1, which is just 1, right? Well, this rule doesn't work in this context, because whenever you're dealing with imaginary numbers, whenever you have a negative in a root where the index is even, that's actually not even defined. So this rule actually doesn't hold for that. It doesn't work. Okay. So, this is where math kind of gets weird, because they're breaking the rules. But again, that's why they call it imaginary numbers. So the definition of I, the imaginary unit, they call it, is root negative 1. All right. So all we're really doing is just defining, new expressions. And the reason we use imaginary numbers is because the operations and the algorithms that are used with these definitions, they can do a few useful things for us. And the operations and the patterns end up being interesting patterns in mathematics. So here's some examples of numbers that are imaginary. You can take I and multiply it by a number, and it's still considered to be imaginary. This is an imaginary, 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 imaginary. Okay. But if you add a number or subtract a number from an imaginary number, then it's considered to be a complex number, because you have a real unit added to an imaginary unit. And to make things even more confusing, they consider these two numbers to both be real. So this number is real, but because it's multiplied into an imaginary number, this whole thing is considered to be imaginary. I know that's confusing, but there, sometimes you just come across things that are confusing in the math curriculum. But just be aware that these numbers are considered to be complex numbers, because you have an imaginary part added to a real number. Okay. So the real number is root 7, and the imaginary is negative 2i, so on and so forth. It's also worthy to note that if you have a number like this, like 10, there's no imaginary part to that. It's just 10. It's just a regular number. That's actually considered to be a complex number. Complex numbers are actually, it's like a big umbrella. It's almost all kinds of numbers. And we're going to talk more about classifying numbers, maybe in a different class in this course. But just be aware that all these numbers are considered to be complex. Just almost every number is considered to be complex. It's under that umbrella. So again, I know this stuff is pretty weird, but the only thing that you have to know is how to actually do the problems. Just follow the algorithms. So we're first going to learn how to add and subtract complex numbers. Now notice that this is a complex number because you have a real part to it and you have an imaginary part to it, and you're adding them. Same thing with here. So this is very, very easy. What you're going to do is you're going to add the real parts. 5 plus negative 1 is 4. And then you're going to add the imaginary parts. 2i plus 3i is 5i. So that's the good news, is that imaginary numbers are very easy to work with. So for number 22, again, you take the real part, negative 3, and add it to the other real part, negative 2, and you get negative 5. You take the imaginary part and add it to the other imaginary part, negative 5i plus 4i is negative I. And there you go. So a complex number plus another complex number is going to be a complex number. Okay, so now why don't you try number 23, and when you come back, we'll do it together. All right, we're back. 8 plus negative 6 is 2. Negative I plus negative 7 is negative 8i. If you got that answer, good job. All right, so why don't you try number 24, and when you come back, we'll do it together. All right, we're back. 1 plus 3 is 4. I plus negative 10i is negative 9i. If you got that answer, good job. All right, number 25, now we're going to subtract. So you have to be very careful with this. Remember, when we're subtracting polynomials, what we're going to do is we're going to, and by the way, I didn't mention something. The only reason that these are in parentheses is that we're trying to show that you're adding one complex number with another complex number. You don't really need the parentheses, okay? Now here, you don't need the parentheses either, but on this one, you definitely need the parentheses because you're subtracting all of this. It's very important that you write the parentheses in that situation, or else your answer is going to be wrong. But you don't need to write it because I'm the one that's giving you the practice problems to begin with. Okay, so now what we do is we can get rid of the parentheses over here. We don't really need those. And what we're going to do is we're going to change this sign to a positive. So the negative becomes a positive. We're going to get rid of the parentheses, and we're going to change the signs of both of these. So this is a positive 4. Not anymore. It's a negative 4 because you're subtracting it. This is a negative 9i. Not anymore. It's a positive 9i. All right? And the rest is easy. You just add the negative part, or the real parts, add the imaginary parts, and you're done. All right? So let's do another one of those together. Again, you can get rid of the parentheses. Change this number to a positive. And you can get rid of the parentheses, and that's a positive 2, but it's going to change to negative 2. And that's a positive 5i, so you're going to have to change it to negative 5i. All right? So negative 1 plus negative 2 is negative 3, and negative 4i plus negative 5i is negative 9i. Okay, so now it's time for you to try. Go ahead and attempt number 27, and when you come back, we'll do it together. All right, we're back. So you can get rid of the parentheses. Change that sign to a positive. And change the signs in this complex number. So now we have positive 7 and negative I. 11 plus 7 is 18. 8i minus I is 7i. All right? So now try, if you got that answer right, good job. Try number 28. When you come back, we'll do it together. All right, we're back. So you can get rid of the parentheses. Change that sign to a positive. And this is a negative 7, so it's going to become positive 7. This is a negative 6i, so it's going to become positive 6i. And then you can just add them. 12 plus 7 is 19. Negative 6i plus 6i, well, they just disappear. So your answer is 19. But remember, any real number falls under the umbrella of complex numbers. This is actually a complex number. You know, all the numbers that we've actually worked with, even back to my arithmetic course, they're all considered to be complex numbers. I know that seems really weird, but you know, there's a lot of stuff that in the math curriculum that may not be exactly obvious. So if you got that answer, good job. Okay, so that's adding and subtracting complex numbers. Now we're going to multiply complex numbers, and you know, these would be considered imaginary numbers also. So this is going to be pretty easy. 3 times 4 is 12. And I times I is I squared, as you can imagine. Now remember that I squared, we talked about this over here, I squared is negative 1. Okay, so whenever you see I squared, it's always negative 1. So that becomes 12 times negative 1. Again, I'm going to highlight that just so you're absolutely clear. That's going to be negative 1. So now we have 12 times negative 1 is negative 12. So that's how you deal with multiplying imaginary numbers. So negative 8 times negative 6 is positive 48. And the I is not really multiplied into another I, so we're just done at that point. Number 31, negative 7 times 4 is negative 28. I times I is I squared. And we get negative 28. I squared is negative 1. Again, I want you to be absolutely clear that's where that negative 1 comes from. Negative 28 times negative 1 is positive 28. And there you go. Okay, so now we're going to use distribution. We're going to multiply this imaginary number by the complex number. So 5i times 3. Remember, this is distribution. 5i times 3 and 5i times 8i. 5i times 3 is 15i. And 5i times, actually, you know what? I'm going to show this. 5i times 3 plus 5i times 8i. All right, and so 5i times 3 is 15i, and 5 times 8 is 40, and I times I is I squared, obviously. And now we have 15I plus 40 times negative 1. And again, just to be absolutely clear, that I squared turns into that negative 1. So let me make some more room here. All right, so now finally we have 15I minus 40. 40 times negative 1 is negative 40. Now it's probably best to always write your solutions in with the real number first, but we don't really have room for that, so I'm just going to leave it in that form. Okay, so now to the next one. We get distribution. We get negative 6I times negative 4, and minus 6I times 9I. So negative 6I times negative 4 is positive 24I, and negative 6I times 9I is 6 times 9 is negative 54. Negative 6 times 9 is negative 54, and then I squared. And then finally we get 24I minus 54, and remember, I squared, that's negative 1. So we get negative 1. And then finally the answer is 24I plus 54, because negative 54 times negative 1 is positive 54. All right. Let's try one more of these before you try some on your own. So now we have I times negative 3 plus I times negative 10I. Okay, so I times negative 3 is just negative 3I, and I times negative 10I is negative 10I squared. And we can't do anything with the negative 3I, but the I squared, you know, that becomes negative 1. Again, that turned into negative 1. And then we get negative 3I plus 10, and we're done, because negative 10 times negative 1 is positive 10. All right, so now it's time for you to try. Go and attempt number 35, and when you come back, we'll do it together. All right, we're back. So 7 times 5 is 35, and the I is not multiplied into another I, so we just leave it like that. So if you got that answer, good job. Okay, 3I times negative 2I. 3 times negative 2 is negative 6, and then I times I is I squared, obviously. But I squared is just negative 1. So negative 6 times negative 1 is positive 6. If you got positive 6, good job. All right, try number 37, and when you come back, we'll do it together. All right, we're back. Negative 5 times negative 7 is positive 35. And I times I is I squared. I squared is defined to be negative 1. That's why it's called imaginary. You can't square a number and get a negative unless it's imaginary. So 35 times negative 1 is negative 35. If you got negative 35, good job. If you didn't get these answers, that's okay. Just go back and figure out what you did wrong. Okay, so now we're going to distribution. Try number 38. And when you come back, we'll do it together. All right, we're back. 7I times 2. And 7I times 3I. 7I times 2 is 14I. 7I times 3I is 21I squared. And I squared is just negative 1. And so our final answer would be 14I minus 21. And let me see if I can fit that on the line there. All right, so we'll go ahead and rectangle that. So if you got that answer, good job. By the way, you don't have to show this step. You can probably go straight to here, and then from there you can probably go straight to there. All right, so try 39, and when you come back, we'll do it together. All right, we're back. Negative 3I times 6. you can do it a bunch of different ways. I'm just going to write a plus. So plus negative 3. Well, I didn't do it that way last time. I guess I'll just do minus 3i times negative 5i. And we get negative 18i plus 15i squared. And we can't do anything with the negative 18i. But I squared, that's negative 1. And so we're left with negative 18i minus 15. If you got that answer, good job. Okay, I want you to try one more of those problems. Try number 40, and when you come back, we'll do it together. All right, we're back. Negative I times negative 4 minus I times negative 3i, and negative I times negative 4 is positive 4i, and negative I times negative 3i is positive 3i squared. All right, so now we get 4i plus 3 times negative 1. And I'm going to move this out of the way. All right, so then our final answer is 4i minus 3. So if you got that answer, good job. All right, so now we're going to multiply two complex numbers. And each complex number, you could call it a binomial. So we're going to have to use FOIL. Remember when we did x plus 6 times x minus 9, stuff like that? And you had to do FOIL. So we had x times x is x squared. Remember, FOIL. And then x times negative 9 is negative 9x. 6 times x is 6x. And 6 times negative 9 is negative 54. These terms usually end up being like terms, so we can add those together. Negative 9x plus 6x is negative 3x. And there you go. So F stands for first terms in the binomials. Multiply those. O stands for outside terms, because they're on the far left and far right. Multiply those. And then I stands for inside terms, because they're right in the middle. And then L stands for the last terms. So again, if you've taken my my previous courses, which are all prerequisites for this course, then you should know that. So now we're going to use FOIL, and I guess I'll write FOIL up here, if that helps. We're going to use FOIL to multiply these imaginary numbers. So 4 times 5, that's F of FOIL. And then 4 times 3i, that's O of FOIL. And then negative 2i times 5, that's I of FOIL. And then we have negative 2i times 3i, that's L of FOIL. 4 times 5 is 20, and 4 times 3i is 12i, and negative 2i times 10 is negative 10i, and negative 2 times 3 is negative 6, and I times I is I squared. Then you have 20. You can actually add these together. So 12i minus 10i is 2i. And then I squared, we learned, is negative 1. Okay, I just want to keep emphasizing that's where that negative 1 comes from. So now we have 20 plus 2i plus 6, because negative 6 times negative 1 is positive 6. Whoops. So now I'm going to make some more room here. And our final answer, we're just going to add the real numbers. 20 plus 6 is 26. And we're left with 26 plus 2i. So that's how you multiply, complex numbers in binomial form. Okay, so let's try one more of these before you try one on your own. So again, 8 times 6 is F of FOIL. 8 times negative 7i is O of FOIL. And then negative 5i times 6 is I of FOIL. And then negative 5i times negative 7i is L of FOIL. 8 times 6 is 48. 8 times negative 7i is negative 56i. Negative 5i times 6 is negative 30i. And negative 5i times negative 7i is positive 35i squared. Okay, so we've got that I squared there. We can combine the like terms. That gives us 86i. And we have 35 times negative 1. The I squared becomes negative 1 as usual. And so we have 48 minus 86i minus 35. And the last step is to combine those real numbers. So 48 minus 35 is 13. And there you go. All right, actually, let's try one more of these before you try one on your own, just to make sure you got it. So we have negative 1 times negative 3, and we have negative 1 times negative 2i plus I times negative 3, and plus I times negative 2i. Now again, you don't have to show this step. You can just, you can jump over steps. That's completely fine. Negative 1 times negative 3 is 3, and then we get positive 2i minus 3i plus, actually, minus 2 I squared. And we can combine the inner terms. 2i minus 3i is negative I, and I squared is negative 1. Okay, so now we're going to go to the right because we're out of room. So 3 minus I plus 2, and 3 plus 2 is 5. So there you go. Okay, so now it's time for you to try. You can take screenshots of those if you want. Again, we're just using FOIL, so it's no big deal. Go ahead and try number 44, and when you come back, we'll do it together. All right, we're back. So F of FOIL is 7 times 7. O of FOIL is 7 times negative 8i. I of FOIL is negative 6i times 7. And L of FOIL is negative 6i times negative 8i. So now we just have to combine those terms. So 49 minus 56i minus 42i plus 48i squared. And combining the inner terms, we have negative 98, it looks like, plus 48 times negative 1. And then we get 49 minus 98i minus 48. And the final answer is going to be 49 minus 48 is 1. And there you go. So if you got that answer, good job. If you didn't get that answer, don't panic. Just go back and figure out what you did wrong. No big deal. Okay, so why don't you try number 45, and when you come back, we'll do it together. All right, we're back. So O of FOIL is negative 2 times negative 1. Or excuse me, that's F of FOIL. And then O of FOIL is negative 2 times 10i. And I of FOIL is 3i times negative 1. And L of FOIL is 3i times 10i. Negative 2 times negative 1 is 2. We get minus 20i minus 3i plus 30i squared. Combine the inner terms, we get negative 23i plus 30 times negative 1. And so on and so forth. Just keep going. And 2 minus 30 is negative 28. And it's always good to write the real number first. That's just the standard way of doing it. So if you got that answer, good job. Why don't you try number 46, and when you come back, we'll do it together. All right, we're back. So O of FOIL is negative 4 times negative 3. Or excuse me, I don't know why I keep saying O. I'm sorry. It's F of FOIL. And then O of FOIL is negative 4 times negative 2i. And then I of FOIL is negative I times negative 3. And L of FOIL is negative I times negative 2i. So now we get 12 plus 8i plus 3i plus 2i squared. And combining the inner terms, we get 11i plus 2 times negative 1. Remember, I squared is negative 1. And we get 12 plus 11i minus 2. Now we have to go to the right because we're out of room, looks like. Actually, no, we're not out of room. And then 12 minus 2 is 10. And that is the final answer. So if you got that answer, good job. Okay, so we're going to do a couple more of these problems, multiplying binomials, but you see now we have something different. We have a complex number raised to the second power. So what does that mean? Well, it just means 6 plus 4i times 6 plus 4i. No big deal. So using FOIL, I'm just going to skip forward here because I want you to see what it would look like if you just skip forward. These problems don't have to take a long time. I'm just going slow because I want you to, understand what's going on. So again, you see how I jump forward there? It's no problem. It's perfectly legal to do. And then we add the inner terms. We get 48i plus 16 times, and we can really jump forward there too. We know that's going to be negative 1, so negative 1 times 16 is negative 16. It's perfectly fine to do that. You just have to show some work. You can't just write the answer because that obviously proves that you didn't do anything. 36 minus 16 is 20, and then we get plus 48i. All right, so why don't you try number 48, and when you come back, we'll do it together. All right, we're back. So we have 2 minus 3i times 2 minus 3i. 2 times 2 is 4. 2 times negative 3i is negative 6i. Negative 3i times 2 is negative 6i. And negative 3i times negative 3i is positive 9i squared. Combine the inner terms, and that becomes negative 9. And just double checking that, so it becomes negative 5 minus 12i, and you're done. So if you got that answer, good job. Okay, on to number 49. So we've added and subtracted complex numbers, we multiplied complex numbers, and now, as you can imagine, we're dividing complex numbers, or a real number with a complex. But again, this is considered complex, so it's the same thing. Okay, so here's the deal. Remember when we had an expression like this with a root, like root 3 minus 2. We didn't like roots in the denominator, so we got rid of that root in the denominator. Well, we have a similar situation here. It's not that we don't really care that there's an imaginary number in the denominator. We don't really care about that. But we do like to write we like to write complex numbers in this form. You see, in other words, we want our numbers to look like complex numbers here. You see these complex numbers? We want them to look like this: a plus bi, a plus bi, a plus bi, a plus bi. You see, we want it to be in that form. Well, this is definitely not in that form. the denominator's in that form, but the whole thing together is not in that form. So we can actually turn this whole thing into a plus bi form by getting rid of the I in the denominator. And guess what? We're going to get rid of that I in the denominator the same way we got rid of the root in the denominator. We're going to do a trick. We're going to multiply 3 minus I on both sides of the fraction. Now, how come we'd have to do it both on both sides? Well, because that's the fundamental principle of fractions. Remember, you can't just multiply the denominator. You have to multiply both the numerator and the denominator, or the fraction is going to change. It's not going to be equivalent anymore. So now, if you distribute on the top, we have 2 times, I'm just going to do this once. I'm not going to do it every time, but I'm just going to show 2 times 3 plus 2 times negative I. Again, we're just using distribution, 2 times 3 and 2 times negative I. And on the bottom, we have 3 times 3, and then plus 3 times negative I, just using FOIL. We have to use FOIL on the bottom. I times 3 plus I times negative I. So again, it's just FOIL on the bottom, just like we did in the previous problems. So now we're going to simplify the bottom, and as you can imagine, the bottom, something special is going to happen in the bottom. First of all, let's do the top. So 6 minus 2i. That's the top. We can't really do much with that anymore. And the bottom, we got 3 times 3 is 9. And 3 times negative I is negative 3i. And I times 3 is just 3i. And I times negative I is negative I squared. But what happens, what's special that happens in the bottom, in the denominator, you can see these cancel out. You got negative 3i and positive 3i. So those cancel out, and you're left with 9 minus I squared. And I squared is negative 1. So in the denominator, we now have a double negative, so we have 9 plus 1. And we have 6 minus 2i is over 10. And now we're going to do something called fraction decomposition. We're going to break this fraction into 2 parts. Normally we don't decompose fractions. But in some parts of the curriculum it's necessary. So these fractions have a common denominator. You can combine them to get this fraction here, but now we're going in the opposite direction. Fraction decomposition is moving in the opposite direction. So now we can reduce the fractions, and we get the following expression. But just to write that in a form that's very easy for us to see, I'm going to put the I off to the right, which is perfectly fine. That's legal. And now we have A plus BI form. A plus BI form. All right. So let's try another one. Again, we're going to change this fraction to A plus BI form. We're going to use the fundamental principle of fractions, which tells us that we can multiply both sides by a number and the fraction retains its value. In other words, the fraction doesn't really change. Its value doesn't change. And notice we have a 2 minus 5i, so we're going to multiply by 2 plus 5i. We have to multiply by the conjugate complex number. Now, typically students will not use parentheses on this other complex number, and that's wrong. You have to use parentheses on this complex number, or else your expression is not correct. So I'm going to multiply the numerator. We get negative 16 minus 40i using distribution. And I'm going to use FOIL here. 2 times 2 is 4. 2 times 5i is 10i. Negative 5i times 2 is negative 10i. And negative 5i times 5i is negative 25i squared. I'm going to write that a little better. Negative 25i squared. Let's continue. We have these inner terms cancel out, so we have 4 minus 25 times I squared, but I squared is negative 1. So that changed to negative 1. And then we have negative 16 minus 40i over 4 plus 25. And 4 plus 25 is 29. Then we just have to use fraction decomposition, and we get negative 16 over 29 minus 40 over 29i. So again, we have b plus, or excuse me, A is the blue part and B is the yellow part, and then of course I. So that's A plus BI form. Okay, so I want you to try number 51. You're going to multiply both sides by 1 minus 2i. And remember to put parentheses on the complex number in the denominator when you multiply it. Try number 51. When you come back, we'll do it together. All right, we're back. So I'm going to multiply both sides of the fraction by 1 minus 2i. And using distribution in the numerator, I get that. And then using FOIL, 1 times 1 is 1. 1 times negative 2i is negative 2i. And 2i times 1 is 2i. And 2i times negative 2i is negative 4i squared. And these inner terms cancel out. And I squared is negative 1. So we have 3 minus 6i all over 1 plus 4. And then of course we're going to separate using fraction decomposition, and we get the following expression. So if you got that right, excellent. Okay, go ahead and try number 52. When you come back, we'll do it together. All right, we're back, so I'm going to rewrite. And then I'm going to multiply both sides of the fraction by 6 plus 3i. And remember, you must write parentheses on the denominator when you multiply both sides, or else your expression is not going to be correct. So again, we're multiplying by the conjugate complex number. So using distribution in the numerator, we get 60 plus 30i over 36. 6 times 6 is 36. 6 times 3i is 18i. Negative 3i times 6 is negative 18i. And negative 3i times 3i is negative 9i squared. So I squared becomes negative 1. And so we have 36 plus 9, which is 45. But we have to reduce and use fraction decomposition. I'll use fraction decomposition first. And we can divide both sides of the fractions. It looks like we divide by 15. So we divide by 15. We get the following. So we got that right. Excellent. So let's try 53 together. Again, I need to write parentheses. And I'm going to multiply both sides of the fraction by the complex conjugate. And I need to write parentheses in the numerator also. What's different about this problem is that we have i's in the numerator and the denominator. You see that? But the process is really going to be the same. It's not going to be much different at all. So I'm going to use FOIL in the numerator and the denominator. So using FOIL in the numerator, I get the following. And then I'm going to use FOIL in the denominator, and I get 4, and then positive 2y, and negative 2y, and then negative I squared. Okay, so let's simplify. In the numerator, the I terms don't cancel out. So these become negative 6i. But in the denominator, the I terms do cancel out. So we have 4 minus negative 1. Again, this I squared becomes negative 1. This I squared becomes negative 1. These inner terms just cancel out. So let's simplify more, and we get negative 8 minus 6i plus 1. That's a double negative and another double negative in the denominator. And negative 8 plus 1 is negative 7. And 4 plus 1 is 5. We have negative 7/5 minus 6/5. So that was again a problem where we had i's in the numerator and the denominator. So let's try one more of those before you try one on your own. If you think you want to try this one on your own, that's fine. But we'll do one more together. Now remember, only change the inner sign. The sign on the I in the case of these problems. Now it is possible for I to be in the front, to be here. Then you would multiply by, or you would go by the rule where you change the sign of the I term, the imaginary number term. Let's double check everything, make sure it's all correct. It looks right. Let's use FOIL in the numerator. And we have negative 27 plus 63i plus 6i minus 14i squared. And in the denominator we have 9 minus 21i plus 21i minus 49i squared. If we add the i's, we get 69i. And minus 14 times negative 1. In the denominator, we get 9 minus 49i squared. And we get negative 27 plus 69i plus 14. Minus 49 times negative 1. And then we get negative 27 plus 14 is negative 13. And then we have 9 plus 49 in the denominator, which is 58. And then we have negative 13 over 58 plus 69 over 58i. And there you go. So if you got that one right, excellent. So you can take a screenshot of these problems if you'd like. And let's try 55. Go and attempt 55. When you come back, we'll do it together. All right, we're back. So we're going to rewrite and we're going to multiply the numerator and the denominator by negative 8 minus I. And as usual, these I squareds are going to become negative 1s. Inner terms are going to cancel out. get 16 minus 6i plus 1 over 64 plus 1. And our final answer, well, not our final answer, but it's going to be 17 minus 6i over 65. And then our final answer is going to be, whoops, final answer, you're going to separate those, so we get 17 over 65 minus 6 over 65i. So if you got that answer, good job. Okay, why don't you try number 56, and when you come back, we'll do it together. All right, we're back. So we're going to rewrite. We're going to multiply both sides by -2 plus 4i. And we get -2 plus 8 times -1, and 4 minus 16 times -1. Again, those I squareds change to -1s. Then we get -2 minus 8 over 4 plus 16. And we get -10 over 20, which is -1/2. So that was an unusual case where we actually just ended up with a regular number. So believe it or not, all that stuff just reduces to 1/2, -1/2. So you got that answer, good job. Now we're going to do some problems that are quite a bit easier, because we don't have a complex number. Well, technically it's a complex number, but we don't have two terms in the denominator. So in order to change this to a plus bi form, we just have to get rid of that I in the denominator, basically. Because a plus bi, there's no I in the denominators. You can't have like a over I plus 3 over 4i. That's just not, it's not the same form. So we're going to rewrite as usual. Let's do this one together. And you don't have to multiply by some weird sum or difference of numbers. You just have to multiply by I, and that'll get rid of the I in the denominator. So then we have, and this is a binomial, so you have to put parentheses. Please put parentheses, or else you're going to get that wrong. So we have 2i minus 8i squared over 3i squared. So now the bottom, well, first let's do the top. So 2i minus 8 times -1, and the I squared in the bottom is also -1. And you end up with 2i plus 16 over -3. Wait, I'm sorry, not 16. 2i plus 8. And then you can just break it up. So we have 2i, and you probably want to change the terms around, because technically we're putting it in that form. So we have -8 thirds minus 2/3 I. You can just rearrange the terms there. Hopefully I didn't confuse you by that. But both of the terms are going to be negative because you're dividing both of them by a negative. Okay, so now it's time for you to try number 58. Same thing, you're just going to multiply the bottom by I. So attempt number 58, and when you come back, we'll do it together. All right, we're back. So I'm going to rewrite and multiply both sides of the fraction by I. I guess I can just put that in parentheses. I don't really need to. I guess I'll just put these in parentheses. I'm going to go down, and we have negative 7i plus 3i squared over I squared. And then you have that I squared. Those I squareds we need to look out for. So now we have negative 7i plus 3 times negative 1 over negative 1. So we have negative 7i minus 3 over negative 1. And when you divide by negative 1, it just changes the signs to positive. So you have 3 plus 7i. Again, rearranging those terms just because we like writing the real number first. So if you got that answer, good job. Now I'm going to use a divider here because this is getting kind of crunched in there. Don't be afraid to use dividers to separate your work. Okay, so if you got that answer, good job. Now we're going to move on to something quite different. You're going to be given these types of problems, and you see them in every textbook, where you have to raise the imaginary number, the imaginary unit, to some big power. And that probably seems pretty difficult. But there's an easy way to do these problems. What you're going to find is it doesn't matter what you raise I to, what power you raise it to, it's always going to be one of these 4 numbers. You see how each of these patterns has one of those 4 numbers? So I to the 8th power is 1. Okay, I to the 11th power is negative I. That's what this is demonstrating. But notice that there's a pattern. You have I, negative 1, negative I, 1. Then you have another pattern, I, negative 1, negative I, 1. It's all the same expression in each one of these groupings of 4. So again, it doesn't matter what number you raise I to, what power you raise the imaginary unit to, you're going to get one of these 4 numbers, either I, negative 1, negative I, or 1. So that means that because there's this pattern, it's going to be fairly easy to find what these expressions reduce to, even though the powers are really high. So let me show you why or where this pattern comes from very quickly. We didn't talk about this when I introduced the imaginary numbers because we didn't ever. It's not really a point in doing it then. We know that I to the first power, obviously that would just be I. And I to the second power, we've already learned that that's negative 1, just by definition. So if we're going to find I to the third power, we just take I to the second power and multiply it by 1 more I. So I to the second power we know is negative 1. And then just multiply that by I. So again, this I squared became negative 1. So negative 1 times I is negative I. So that's how we find I to the third power. Now I to the fourth power, you just take I to the third power and multiply by another I. And we know I to the third power is negative I. And so you multiply negative I times I is negative I squared. And I squared is negative 1. So you're just left with 1. All right. Now, because you're at 1 now, you went all the way to 1. So now, if we go to the fifth power, you just take I to the fourth and multiply it by 1 more I to get I to the fifth. And we just found that I to the fourth is 1. So 1 times I is I. And notice that when you go to I to the fifth, you're just starting over again right back where you started at I. You see? So the pattern just starts over again. So again, you had I, negative 1, negative I, 1. Then you're going to have the same pattern. I, negative 1, negative I, 1. And the same pattern again, and the same pattern again, and the same pattern again. So that's why you have this pattern. Look up here in the yellow and the purple and the green and the orange. You have that same pattern of 4 numbers when you raise I. You just keep going higher and higher and higher, but you have the same 4 numbers. So that's going to make it really easy for us. So here's the easy way to do this. we could go into a lengthy explanation of this, but probably the easiest way is just to use this general rule here. What you want to do is you want to take the power and divide it by 4. Why 4? Because there's 4 units or elements in each pattern. And you're going to figure out what the remainder is going to be. So 4 goes in 6 times. 6 times 4 is 24. Whoops. 24, and 26 minus 24 is 2. So the remainder is 2. Okay, so notice in the yellow it said if the remainder is 2, then the answer is -1. And that's it. The answer is -1. If the remainder is 0, the answer is 1. If the remainder is 1, then the answer is I. And if the remainder is 2, the answer is -1. And if the remainder is 3, the answer is -I. So that's just how this works. Once you get the hang of that, then you can see that this is really not difficult at all. So for 35, number 60, we're going to raise I to the 35th power. And we're just going to take 35. And again, we always divide by 4. 4 goes into 35 8 times. 8 times 4 is 32. Remainder is 3. So now our remainder is 3. So notice in the purple, if the remainder is 3, then the answer is -I. So I to the 35th power is -I. That's simple. Whoops, I forgot to rectangle that answer. So again, if you just follow that rule, this is pretty easy. Again, it's all based on the idea that, let's give an example here. Let's see, it's kind of hard to demonstrate with these because there's so many groupings, but you're going to have, what this means is you're going to, for problem 59, you're going to have 6 groupings of 4. 1, 2, 3, 4, and then another grouping 5, and then the 6th grouping, right? Then you're going to have a remainder of 2, which means, again, in each one of these you have I, -1, I, -1. So a remainder of 2 means after multiplying by all those, you get 1 in the last element here. You have I, -1, -I1. So after raising to the 24th power, you get 1, but then you do 25th power, which gets you I, and then 26th power, which gets you -1. Okay, so that's why when the remainder is 2, you always get to -1. All right, so that's all that this is trying to explain with all this writing. Okay, so let's try number 61. So I to the raised to the 80th power. You're going to take 80 and you're going to divide it by 4. 4 goes into 8 2 times. 4 times 2 is 8. Bring down the 0. 4 goes into 0 0 times. And the remainder, as you can see, is 0. So if the remainder is 0, that's the blue. It says if the remainder is 0, then the answer is 1. So I to the 80th power is equal to 1. Okay, so why don't you try number 62. You're going to take 20, divide by 4, and figure out what the remainder is, and this is going to tell you what your answer is. It's either going to be I, -1, -I, or 1. Try number 62, and when you come back, we'll do it together. All right, we're back. So we're going to divide 20 by 4, and it goes in 5 times, and you can see the remainder is 0. So in the blue there, it tells us that our answer must be 1. So if you got that answer, good job. Okay, try number 25, or excuse me, try 63, raising I to the 25th power, and when you come back, we'll do it together. All right, we're back. So we're going to take 25, the power, and divide by 4. You're always dividing by 4. 4 goes into 25 6 times. 4 times 6 is 24. 25 minus 24 is 1. The remainder is 1. But if the remainder is 1, the green tells us that the answer must be I. So I to the 25th power is I. So if you got that answer, good job. Try number 64, and when you come back, we'll do it together. All right, we're back. We're going to take 75, divide by 4. Always divide by 4. 4 goes into 7 one time. 4 times 1 is 4. 7 minus 4 is 3. Bring down the 5. 4 goes into 35. 8 times. 4 times 8 is 32. 35 minus 32 is 3. The remainder is 3. So the purple tells us that if the remainder is 3, then the answer is -I. So if you got -I, good job. Again, these are just kind of tricky problems that are designed to be intimidating, but as you can see, they're pretty easy. Every textbook has these problems, so you're just going to have to know how to do these. All right, so we have a few more things to do today. here we're supposed to take these expressions and write in terms of I. So you always deal with an I when you have a negative inside of a square root, like this example. Well, that's the example I actually wrote. So we can actually take this expression and write it in terms of I. So what we're going to do is we're going to factor that expression to -1 times 3, and then we're going to break it up into two parts, root -1 times root 3. And remember, root -1 is defined to be I. See, we define that over here. I is root -1. So, let me get back over there. We can just say that root -1 is I, and there you go. So long story short, if you have a -1 in a square root symbol, the -1 just comes out as an I. You see that? So remember, you're probably thinking, wait a second, this didn't hold before. When we had square root A times square root B, it didn't equal square root A times B. Well, that's true, but when you're going backwards, in this situation, it actually does hold for complex numbers or imaginary numbers. So again, we can just factor out -1 times 81, and then we have root -1 times root 81. Root -1 is just I, and then root 81 is 9, and usually the coefficient comes first, so we can just write it as 9i. All right. So, the same situation occurs here. You can really just take the I out. You don't have to go through all that if you don't want to. And root 4 is 2, and again the I just comes out. Okay, now time for you to try. Again, if you want to show the work, you can, but you don't really have to. You can just take the -1 out as an I. So try 69, and when you come back, we'll do it together. All right, we're back. So just to show you the work, in case you want to see it, separate those. We have root -1 times root 5, which is I times root 5. And you might think, well, don't we write the root 5 first? Well, you could do that, but that's pretty dangerous because then the I might look like it's inside the root, and that can get pretty bad. So I just put the I in front. So if you got that answer, good job. Try number 70. When you come back, we'll do it together. All right, we're back. So again, just showing the work here. We don't really need to show it, but factor that, and then you have root -1 times root 49. Root -1 is I, and root 49 is 7. Put the coefficient in front, and you're done. So if you got that answer, good job. Try number 71, and when you come back, we'll do it together. All right, we're back. We're going to take the negative out as an I, and you're pretty much done. Again, you don't have to show the work. Try number 72, and when you come back, we'll do it together. All right, we're back. So you're going to take the -1 out as an I, and root 100 is just 10, and just flip those around. That's the traditional way to write it. So if you got that answer, good job. Okay, just a few more problems here. So now we're adding and subtracting these expressions. So we want to factor. We're going to factor to -1 times 4 times 5. And then here we're going to factor to -1 times 9 times 5. So just like in the other root problems we had in previous classes, we'd like to combine these terms, but the problem is we can't because they're not like terms. We're going to make them like terms. In these particular problems, that's possible. So now we're going to separate. And again, once you get the hang of this, you don't really have to show all this. So then we have root -1. That just becomes I. And root 4 becomes 2. And root 5, I guess I can write dots for multiplication. Root 5 you can't do anything with. And so again, the root -1, that becomes I. Okay, so 2 times 5 is 10. Whoops. 6 times 3 is 18. And notice we're adding apples with apples. We have 10 apples plus 18 apples. They're both apples, I root 5s. So that would be 28I root 5. 10 apples plus 18 apples is 28 apples. Okay, let's try one more of these before you try one on your own. We're almost done with the problems today, so let's do this. So we're going to factor 8 so it has a perfect square. So that would be 4 times 2. Again, you did this in your previous classes. And negative 1 times 16. We're going to need 16 on this one. And so we get root negative 1 times, separating the root 4 times root 2, root negative 1 times root 16 times root 2. So we get negative 3 times I times 2 times root 2 plus 2 times I times 4 times root 2. Negative 6I root 2 plus 8I root 2. And I designed these problems specifically so that you get apples and apples. We have I root 2's. Negative 6I root 2's plus 8I root 2's will give you 2I root 2. And that's the answer. Okay, so you're going to try 2 of these problems. You can take a screenshot of that if you are confused by that and you want to use that. So you're going to try 2 of these problems, and then we're going to be done for the day. All right, so go ahead and try 75, and when you come back, we'll do it together. All right, we're back. So we're going to factor. And we have to factor the negative 1 out, too. So we get 8 root negative 1 times root, times root 9 times root 3 times root negative 1 times root 4 times root 3. And we get I so on and so forth. Very important to understand that root negative 1 became an I. Okay, so now we get 24I root 3 minus 4I root 3, and we have I root 3, so 24 of those minus 4 of those is 20I root 3. Again, you're subtracting apples, which is perfectly legal. So if you got that answer, good job. Now try number 76, and when you come back, we'll do it together. All right, we're back. So we have negative 1 times 25 times 10. Again, you have to factor, so you have a perfect square there. And negative 1 times 4 times 10. And separating. And so these root negative 1's become i's as usual. And so now we have negative 5I root 10 plus 2I root 10. And those are like terms. So negative 5 plus 2 is negative 3. And that is the answer. So if you got that answer, that's a good job. Okay, that was the class today. Let's take screenshots of all the work that we did to help you with your homework or to study for tests. So this is screenshot 1 and screenshot number 2 and screenshot number 3 and screenshot number 4 and screenshot number 5 and screenshot number 6. But don't go before you get your homework. Let's take a look at the homework. Here's the first 2 pages of the homework. So get a screenshot of that. And here's the second 2 pages of the homework. Get a screenshot of that. So get that homework done completely, correctly, neatly, and keep it in correct chronological order in your binder. And if you don't do the homework, remember, it's a 100% guarantee you're going to learn nothing in this course. So get that homework done, and I'll look forward to seeing you in the next class.